Okay, hello, welcome back. So now we are going to study the the easiest case of impact, and that is central impact. So for simplicity, well, we always assume kind of round spherical objects. They don't have to be, as long as the conditions of central impact are satisfied. But in this cartoonish example, let's assume everything is round. I have two bodies, body A and body B. They are happily moving around and they are approaching each other. VA must be, the velocity of A must be bigger than VB, such that it eventually approaches and makes contact. And here, for the rest, I have drawn the events as time progress. So this is kind of time. These are different phases that we can define contact and the entire impact. So as body A approaches body B, eventually it comes to contact. And in this case, let's draw it here. These are not forces, these are velocities. But B will have VB1 before the contact, and body A will have VA1. So that's where contact begins. After that, anything that happens during contact, we are analyzing it, but the end result is that what happens in between is the duration of an impulsing force being active. So this is impulsive forces are active. So the end result we are trying to find is how we can calculate the conditions of at the end of impact using the information at the beginning of impact and skip the procedure that I'm going to do next for our calculations. So that is our goal. Our goal is to find final contact conditions given the initial contact conditions. Okay, let me explain what is happening during contact. So as bodies start to make contact, because body A is going it's going faster than body B, it starts to push into body B, and the two bodies are, in reality, the two bodies start to deform. And in this case, you can note that body A is pushing body B inward, and the reaction of that body A is pushing body B is pushing body A back. Essentially, it's trying to slow it down. And these two forces, it is, well, as you will see soon, let's call this force P, but we work with the impulse of these forces, PdA. So these impulses are active. Body B is going to speed up. Body A is going to slow down until you reach a point that you are maximally compressing the two bodies together. And in this case, both bodies will have the same velocity, that is relatively big, same velocity. VA is VB equals some common velocity, because if they are not the same, means that A is going to push further into B until this happens. So it is guaranteed that at some point during contact, we will have a time that the two bodies move with the same velocity, and that is when we have maximum deformation. And after that, all these elastic energy stored in these two bodies because they are being compressed start to release. And now let me color code this. Wait, I'm going to make this green is P dt. Why did I write dA here? Oh, it's so difficult to. This is dt. And blue is from. Green is from A to B. Red is B to A. So now, body B. Let me see. Yeah, it's good. Yes, it's good. Now body A is going to push body B out. So let's call this with R dt. R is a restitution force. And body B is going to create an equal but opposite impulse, R dt, in the opposite direction. And body B starts to being pushed forward, gaining speed. Body A is going to continue being pushed backward, losing some speed. And until the two bodies are fully back to their original shape. And that is when they lose contact. And in that case, what is happening? In this case, B will move with VB2, A will move with VA2, and contact ends, and you can go and happily study what happens after. So what is going on in between? We mentioned that all these forces, P and R, are huge forces that are only active during a very short amount of time. So during this time of contact, we can safely assume the total momentum of the system is conserved. So during contact, momentum conserved, and that means mass of A times V of A at the beginning plus mass of B plus V of B at the beginning must equal the final condition, mass of A, VA2 plus mass of B, VB2. So that is one equation we have to relate what happens before contact to what happens after contact. But note that these two are unknowns, assuming that we know the initial conditions before the contact. So we know these. One equation, two unknowns, we cannot solve it just like that. We need another piece of information. And that information, you have to gather it experimentally. We need another information, and that is essentially related to how much energy you lose during contact. But we want to define it. Let's define coefficient of restitution. We use letter E, and that is defined as the size of these restitution impulse divided by how much you had during compression, P dt. If these two impulses are the same, essentially it means that whatever you put in during compression, you get back during restitution. But often it is a case that the materials have some internal damping. You can assume a rubber that as you compress it, when you release it, the amount of force or impulse you get is slightly smaller. So this E is usually less than 1. It's always less than 1 in passive contacts. And you have to calculate this or measure it experimentally. Every contact, every material, every shape, even conditions of impact are different. For instance, if the initial velocities are different, this E could be slightly different between conditions, but we can know, at least for many of the materials and conditions, we have good estimates of this E value, the coefficient of restitution. So how do we use this to solve our problem of one equation, two unknowns? You can note that during deformation, during the deformation phase, you can write the impulse and linear impulse and momentum principle. So let me make this phase 1, and this will be phase 2 during restitution. Yeah. So during deformation, before deformation, you have, let's look at any one of the bodies. In this case, I'm going to look at body A. MA VA1 plus the impulse acting on it, PDT, equals MA V, this common V, common velocity V after the end of deformation. But note that this impulse is negative because it is in the opposite direction of our positive definition of, well, which direction is positive. I've taken this direction to be positive. And similarly, during restitution, we start with MAV, this common velocity, plus this RDT, again it is negative, gives us MAVA2. You can write exactly the same thing for body B, and BVB1 plus integral of PDT. But this time it is positive because the impulse is in positive direction, equals MA, MBV. And during restitution, we can write MBV plus integral of RDT equals MBVB2. And now we have a whole bunch of equations with some manipulation and so on. You can finally write E. So you have to calculate these or eliminate these impulses. You will end up with E being VB2 minus V divided by V minus VB. Wait a second. Let me double check what I have. VB2, VB1. No, that's. Oh, yeah, okay. Yeah, let's not do that. Let's go one further ahead. Don't worry about this intermediate step. What really happens is E becomes VB2 minus VA V2 divided by VA1 minus VB1. This is better. So what E really is? Relative velocity after impact divided by relative velocity before. So if you know experimentally what E is, the coefficient of restitution, like it is given to you, you cannot kind of know it yet. The problem has to give it to you. You know it is 80% or 0.8. You can know the relative velocity VB2 minus VA2 after the impact is 80% of the relative velocity before impact, and combine it with the information about conserved linear momentum, you can calculate what happens after the impact. So very long story, but the end result is that you can skip all the calculations, what happens during contact, and knowing that it is an impulsive situation, impulsive force situation, you can know the velocities before the impact using these two boxed equations, calculate what happens after the impact, and once you have the post-impact condition, you can then go and calculate what happens next using any other method like work and energy or equation of motion and so on. And you don't have to worry about all these derivations in the middle. So that is all I wanted to say, I think. Let me double check. Yeah, I think that is all I wanted to say. Yeah. So you can now solve central impact problems. And in the next video, we'll see what happens when we have oblique contact. Let me see. Actually, I have some remarks here. Oh, they were very important. I missed this one. Ooh, let's do this. So because it's related, let's make it like this so it looks nice and cute. So two very important impact conditions is when E equals 1. That is what we call purely elastic or elastic impact. Contact or impact. In this case, the relative velocity after is going to be exactly the same as relative velocity before. And if you do the math, you will note here that let's do it this way. Total kinetic energy remains the same. So in elastic impact, you don't have energy loss. So sometimes the problem phrase it that there's no energy loss during contact. You can know it is an elastic impact, meaning that the coefficient of restitution is 1. But in reality, always E is less than 1 because you don't have perfectly elastic impact. There's always a little bit of energy loss whenever you have these contacts. The other limiting condition is when E equals 1. This is called purely plastic impact. And note that if E is equal to 1, looking at this equation, you will see that VB2 minus VBA2 must be 0. In other words, the two bodies will move together with the same velocity after the impact. Essentially, they are smooshed together. And they fully deform, no restitution whatsoever, and they continue moving with the same speed. In that case, essentially, the contact ends here after maximum deformation. Now I don't want to mess up my notes too much. Okay, these are very two important definitions when it comes to contact. Well, let me finish this sentence. Contact, or no, wait, impact ends. Impact ends at max deformation, and the two bodies move together with the same speed. And in this case, a lot of energy is lost. A lot of energy, kinetic energy is lost and turned into heat. Okay, that is finally all I wanted to say. All right, good. I'm glad I mentioned these. So next time, oblique impact. See you then.